Okay. So in last class, last lecture video, we mentioned this. We say this x bar follow normal distribution, right? Okay. So we just prove this. Okay. So x bar follow normal. So this is just the foundation in statistics. So from here uh, we can we can draw this method, that method. Okay. So also from normal distribution, we can produce many other distributions. So normal is very important. So the other is about in statistics, our first question is estimation. So estimation is meaning like from, okay, so story just like that, from there's a population, from a population we take a sample, right? Take a sample. So from sample, we can find a sample mean x bar, right? So this x bar will follow normal. So so here is the starting point for statistics. Okay, and for estimation, meaning like for population, we have population information like average, population average mu or population's mean, and population's standard deviation sigma. So once we have those data, right, we have those data. So how can we estimate this mu and sigma? Okay, so like from population, from sample information, how to estimate this mu and sigma. Okay, so we say estimate mu and sigma. We have this simple ways we call point estimation. Point estimation basically just we just let samples like almost equal populations populations things. Now like a samples mean equal population mean. Samples standard deviation equal population standard deviation, right? So from sample we have x bar sample mean. So we just let the sample mean and population mean equal. And from sample we have samples standard deviation is, so we just let this equal populations standard deviation sigma. Okay, so those are point estimation. For this x bar and s, we have the formula. Okay, x bar and s. So let's say from the data, suppose data is just x1, x2, and xn. Oh, this data just like sample, right? So from sample we have those data, those numbers. Then this x bar is calculated this way, right? Equal, we just add them up, x1 plus x2 plus xn divided by a, right? Sample mean, and then sample standard deviation or sample's variance. Sample's variance is square equals thus summation xi minus x bar squared. Then I start from 1 to n, like x1 minus x bar squared plus x2 minus x bar squared, like the then divided by n minus 1. Okay, so we claim this. We say so the formula best formula, or source estimations best. We basically saying the formula the best. Formula is the best, and the estimate we just use we use a's to estimate sigma, use x bar to estimate this mu. So those estimation is the best. We say such estimation is the best. Okay. So in applied stats we explain this, like y like a square samples variance. So here just divided by n minus 1, not n. So why we explain this? Because this n minus 1 is a degree of freedom. So right, should divide by degree of freedom. But we still do not explain why. Why should divide by degree of freedom? So now we can say like because divided by n minus 1 is better than divided by n. Okay, so those formula are the best one. Okay, like x bar, use this to estimate this mu is the best way. Okay, so now we have big questions. What best meanings? Right. So here we have solved the question. First one is what do best meanings here? Does best meanings what does best mean? Also here we need a definition like what best means. Okay, we need a clear terms to judge this is better than that, or this is best one. Okay, so the first question, what best meanings, and the second question, let's say we put this question 1, this is question 2. So how to derive the best, how to get the best one, to get the best estimate. How to get the best estimate for something. Okay, and the other questions maybe best estimate not always exist, right? But anyway, like let's say so those are also like two bigger questions. What does best meanings? So let's explain the first question. So we say first question, answer 1. What the best meanings? First one we say, let's say, suppose like we wanted to estimate something, so we call something for population is parameter. Anything from population we call parameters. And anything from sample, from data, like from data, from those numbers, we can define this. We can get this one, get that one. So we call those statistic. Okay. So for example, let's say, like for this, let's say for this population's mu. Suppose data we have this. The data is we have x1, x2, x3. Okay, those are data. So with those data, we want to estimate this mu. So we can use this. We say like we can use x1 as estimate for mu hat. We just use first number to estimate this, or use the average for all, or average the x1 plus x2, average for those two to estimate. We regard this as estimation for population's average, right? Or we also can use this average for all. We use this to estimate populations. So mu hat means like estimate for mu. So which one is the best? So roughly we can say, suppose this is a mu, like we say we put this as a mu hat 3 so the estimate for mu, this is mu hat 2. So mu hat 3, this one it seems better than others too, right? We can say roughly mu 3 cat this is better than mu 1 hat and mu 2 hat. So why? Because like we say like mu 1 in mu 1 we only use x1. We forget the information from x2, x3, right? And mu 2 hat we just use x1, x2. We do not use the information from x3, right? So for this mu 3 hat, it seems we use all of them. We use x1, x2, x3. But here, why divided by 3? How about divided by 2? Let's say, okay, this one, x1 plus x2 plus x3 divided by 4, I say. We use this to estimate population's average. So this one, we still use this all information. So we all use these 3 data. We all those data, right? We do not. We use all of them, but divided by 3, or why divided by 4? Or divided by 3 is better than divided by 4. The same. Okay. So from here we define so we judge the which estimator is better. So requirement is So we say, so we can define the best estimate. So for best estimate, like let's say for mu hat, for mu, we just consider this, like we use this to estimate like mu, like we use those to estimate population's average. Okay. So the requirement for best estimate, first one we say should be on first requirement, unbiased. Says first requirement. So what is biased or unbiased meanings? Meanings like, let's say, so we can regard it as this formula, like let's say, like we just regard the formula is a method for estimation. So if we take this 3, so divided by 4, we use this to estimate this. So let's say, so suppose like a true value is here. So according to your method, according to your formula, sometimes so cannot be exactly equal. Sometimes you estimate it here a little bit high, sometimes a little bit less, sometimes a little bit higher. But on the average equals this. So this is called unbiased. So in terms of thus, we say average or expectation or average by now means like mean, right? We say mu hat will equal mu. Okay, so this is unbiased. Okay, so this is first requirement. So we can say like, okay, so compare. Okay, so let's say compare mu4 and mu3. We can find mu4 is biased, not unbiased, because we say like, let's say, so x1, x2, x3 all come from the same population. So we have this, we say x1 so equal mu, right? We regard x1 this also can change. So x1 just come from that population. So it's average x1 take x1. So here x1 just take a number. Take a person from the population, right? So sometimes a little bit high, sometimes a little bit low, the average. But on the average, so because like this from the, like we say from this population take x1, right? Okay, so we have this like, so if population average mu, then x1 equal mu, and x2 is also mu. So we can find, let's say, so x1 plus x2 plus x3 over 4 equal, like we can take 4 other side equal 4 over 1. So x1 plus x2 plus x3, right? So x1, okay, so this is just equal x1 plus x2 plus x3. So each one is mu, so this equal like 3 over 4 mu. So this is not equal mu, so we say this estimate or this formula is not so good, is biased, not equal mu, right? But this one, x1 plus x2 plus x3 divided by 3. So this is unbiased, right? So we say mu4 is better than, mu3 is better than mu4, like here. Mu3 is better than mu4. So we can say why the one, because mu4 is biased, mu3 is unbiased. But we can see, but we can find like mu1, like mu1 hat, mu2 hat, this mu3 hat. These three estimators are all unbiased. So for these three, which one is bad? We say, so let's put it to here. We say, so we can claim like mu1 hat is thus just equal x1, and mu2 hat is thus x1 plus x2 over 2. Mu3 hat x1 plus x2 plus x3 over 3. We say all are unbiased. All are unbiased, right? Okay, so among unbiased, so we say mu3 is better than mu1, mu2. Because we say, because let's say, so all are unbiased, but let's say compared to estimate, let's say true value suppose here. So for this method, estimate is mu sometimes here, sometimes here, sometimes here, sometimes here. Okay, so for this method, true value is here, sometimes estimate here, sometimes here, sometimes here, or sometimes here, but the average is here. So both of them unbiased. But we say this one is bad, right? Because it changes small here, changing is big, So we say, so we just check the variance. So we say this variance is small, is big, changing is big, right? So so compare unbiased, which one is best? We just check variance. So we can confirm the variance for mu2 hat. So it's bigger than variance of mu3 hat. And I think, let's say, variance for mu1 hat is larger than this. Okay, so compare mu1 hat, mu2 hat, and mu3 hat. We say mu3 hat is the best. Okay, is better. Yeah. So the best estimate. So we can define a best estimate. Best estimate is first one is unbiased. There's a first requirement, right? And the second one is minimum variance. Variance is the smallest among all unbiased estimators. So we put them together. We call those as U M U E. So this equal U means unbiased minimum. I'm sorry, V minimum and variance. V means variance estimate. Okay. So UMVE. So this is best. So now, we wanted to prove. X bar is UMVE for mu. So X bar is the best estimate for mu. So we can say samples mean is the best estimate for population's mean. Okay, and also we wanted to prove like this sigma or s square. We just say this samples variance is an UMVE for just sigma square. Okay, so population sample, this formula is best. So population samples variance as estimate for this is the best estimate for population's variance, right? Okay. Okay. So how to prove? So let's say like how to prove X bar is best. So let's say okay. So here we for X bar, I think it's easy to prove. But in general, we like let's say in general, this is not easy question. Like how can we prove some estimate is the best estimate for population's parameter? So this is not an easy question. Okay. Let's say. So the other. So at first, let's say, for let's prove this like for X bar is the UMVE for mu. Maybe this one's okay, little bit easy, but for is square, like samples variance is the best estimate of population variance. This is not so easy. Okay, and so but anyway, like let's prove X bar. Okay, X bar is best. Okay. So now we wanted to prove. Okay. We just prove. We say focus on proof for this one. Like X bar is UMVE for mu. Okay. Okay. So let's say so suppose we actually like x bar, we can look at we write x bar as like x1 plus x2 plus xn over n. We can write this as this, like equal 1 over n x1 plus 1 over n x2 plus 1 over n xn, right? Okay, so let's consider general situation. We say we have a combination for x1, x2, xn. We say we have this. Let's say we have this estimate. This is a linear combination for x1 to xn. So that's equal, let's say, a1 x1 plus a2 x2 plus a n xn. So this ai coefficient should be cannot be negative, right? So positive, okay, at least the 0. So at first we say this mu hat should equal mu, right? So unbiased. First requirement is unbiased. First requirement is unbiased. So for unbiased, so then satisfy this requirement. What is the condition for a1, a2, an? So we have actually we get this because this is mu bar equal a1 x1 plus a2 x2 plus an xn. So for expectation for we have this just equal a1 is x1, right, plus a2 is x2 plus just like that plus an is xn. So this is x1 is x2 is xn all up equal mu. So this is just equal a1 plus a2 plus an mu. So this equal mu, we have a requirement. So we have this. So a1 plus a2 plus an equal 1, right? We have this first requirement, so unbiased requirement. Then let's check variance. What is variance for mu1 hat? No, for mu hat, not mu1, for mu hat. So variance for mu hat is a1 x1 plus a n xn, right? Okay. Okay. So for variance, we have this formula. We have this formula. Let's say variance just square, just like that, square. Let's say we have this variance for ax plus by. So here x and y are random variable. If they are independent, then we have this formula. So just let's square. So this equal, actually equal Okay. Oh, I'm sorry. Oh, mm, no, I'm sorry. Mm, oh, well, ah, let's say my pen goes to there, yeah. So I don't know how can we. Okay. Mm, let me see. Oh, equal. Oh, it's not so good. Yeah. Oh, okay. Yeah. Okay. So by now it's okay. Maybe the pen goes to here. Yeah. So Vax plus by, we have this formula equal a square Vx, variance of x, plus b square variance of y. Okay. If they're independent. Okay. Okay. So now let's say, so this variance for variance for mu hat. So we can say this equal a1 square, so vx1 plus a2 square vx2, right? Plus an square vxa. Okay. And this vx1 variance for x1, variance for x2, variance for xn, same, because x1, x2, xn are from the same population, or they follow the same distribution. Their variance is sigma square, right? So we have this. That's equal a1 square plus a2 square plus an square. So sigma square. So here sigma square is fixed. Sigma square is fixed. So the question is, so how can you choose a1, a2, a like, until an, such that we have those math problem, such that a1 plus a2 plus an equal 1. We have this condition. We want to make this a1 square plus a2 square plus an square. We make this as small as possible, minimize this. So when for what a1, a2, an that can minimize this. So this become math problem. Okay, so we already proved, use some mathematics. We show this only. So we say only this condition, only this case, a1, a2 all equal 1 over n. So there's a solution. When all a1, a2, an equal, and they're just equal 1 over n, then a1 square plus a2 square plus an square is smallest. Okay. So let's confirm this. Let's say, let's say, if we just say a1, let's check this. Like suppose let's say a1, a2 like a half. Like this, just check this. Like mu2 hat is equal x1 plus x2 divided by 2, right? So this we say add them up equal 1, yeah. Add them up equal 1. And their square, the value is this square plus this square equal, we say equal what? Equal 1 over 4, 1 over 4, 1 over 4 plus 1 over 4. So in this case, 1 over 2, right? So sum of their square is 1 over 2. So how about, let's say, how about this one? 1 over 3 plus 1. 1 over 3, 1 over 3, 1 over 3. These 3 numbers, add them up equal 1, right? And their square, let's check this square plus this square plus this square. We find this equal 3 times, yeah, 1 over 3 squared, 9, so 1 over 3. So 1 over 3 is smaller than this, right? Okay. Okay. So here it seems like so here if we can select if this mu, this estimate is a linear combination just like that, if mu hat uses this, okay. If in this case, then we say a1, a2, an equal 1 over n is best. But we still have other question, like how can you just use the linear combination, right? Maybe the best estimate is not in this form, in other form, right? So we still have the problem question, how to find the best estimate. Like we have data, from data you can do many things. We can produce many things to estimate this. Like, so let's say, suppose the data is just those numbers, x1, x2, xn. So from the data, you can produce many things. You can produce like x, you can produce this those xn over 2, right? Over n. This is like linear combination for x1, x2. Or maybe the best estimate could be like this: x1 square plus x2 square plus xn square over n, right? Okay, so here we still have this question: how to get a good estimate? How to like derive the formula? How to get a reasonable estimate? A good or reasonable? We just put a good estimate. How to? So we can use this. We can get this formula, that formula. We have too many possible ways. So how can we how can we derive a good estimate? How to estimate? Okay. So there's a question saying, once we find use some method to get some estimate, we want to check whether this is UMVE, whether this is the best one, or maybe let's say we can check this question, how to get the best one. We have solved the question, right? How to get UMVE. So this is also a big question in mathematical stats. So we will leave this for next class. Okay. 好，next class we just do this. Once we have data, like x1, x2, xn, we have the data. So how to derive the formula to estimate this mu or estimate other things, estimate the parameters. Okay. Okay. So we can stop here. Okay. So see you. So thank you for watch.